because I didn't see it. Because of that, I wanted to, check my homework. And after this class, I tried to finish it earlier.
Okay.
So,
I can post. Yeah, I can post more class notes and also the homework assignment. Yeah, I can do that.
I mean, yeah, I don't see like adding for the second time my assignment. I think it's closed for that.
Okay. Uh,
Thank you.
okay. So, any other questions? Okay. So let's finish up the topics in the module 7. Um, so in module 7, in the last slide, we have two examples, example 5 and example 6. Um, so these two problems are basically a kind of like opposite problem. So example 5 is to build the deterministic of finite automata. So DFA for language L, which is set of all. Okay, so L is a set of all string over 0 and 1 that contains the string 0011. Okay, so that means we need to build a DFA that um, to accept the languages, accept all the strings that contains the substring 0011. So we did that. So there are actually a total of 5 states: A, B, C, D, E, and the E is the final state, the accepting state. And we start with A. So we want to find a substring which contains 0011. So that's why in order to build this DFA, the first thing we want to do is suppose we actually start with A, and the first import is 0. So then, which is good. 0 is part of the substring 0011. So we actually move 0 to B, so which is actually one step closer to the accepting state, right? Now, if the next zero import is happen to be 0 again, so we are actually one more step closer to the accepting state. Okay, suppose we're lucky, so all the actual import actually are you know part of the string. So 0011. So we have 0011. So we have 0 goes to state B. We have another import 0, and then we go to state C. And we have next one 1. Then we go to state D, and then another 1. So we actually go to the acceptor state, which is E. Accepting state, which is E. Okay, that's the actually best scenario. So we just got the 0011. Now, but things are not going to be always like this. So what about if the first import is 1? If the first import is 1, which is not going to be contributed to these 0011 substring. So in that case, we're going to say, okay, we're going to actually still going to stay with A because we're not going to move forward. Now, once we find the 0, then we move forward. But we move forward to B. Now, if after B, the next import is 1 again, so that means 0, 1 is not going to make up this X0011 string. So that means everything we have done so far are pretty much wasted. So we have to actually build another 0011 string. So in that case, if the next one is 1, so we have to move back to A. And then we try to start over again. Okay. All we want to is we want to, create a string 0011 and 0 and the 0 and then right after 0 going to be 1 and going to be 1. So if there's something actually happens in between, then we have to start over again. So if it's 1, then we start over again from A. Now, if we are lucky, so we have actually go to 0, next import is 0, next import is 0. Okay, so we reach the state C. Now, if the next state is import is again, it's 0. Now, this is not going to actually move closer to the accepting state because we already have 0, 0, and next one we expect to see is 1, but it still have 0. So in that case, so we basically shifted this string forward, and we're going to count these two as part of the 0011 string. So then if we stay with, if we got a 0 import, so we stay with C because we already reach 2, 0 now. So the next two imports we want to build is 1 and 1. So if it's not 1, then we still stay with C until the next one is 1. Okay. Now, if we got one more 1, another 1, then we're done, right? We successfully has, build a string which contains 0011. But if we are unfortunate, we actually got a 0 again. So that means it's a 0010. That's not good. So we have to actually start over again to build another 0011, right? So in that case, we have to roll back because we already have a 0 now. So all we need to do is we hope that we can get another 0, right? So we just roll back to B. So now B to C, if it's 0, then we're back to C again. Okay. Now if we continue to get 0, stay in the C, and then sooner or later we will reach D, and if we're lucky, the next one is 1 again, so we reach E. So now after we reach E, that's the accepting state. Then once we got the accepting state, then any other import values we actually get never going to actually have any impact on the string because the string is already accepted. So we just need a string that contains 0011. Okay. Now, if we say we want to build a DFA for language L, which is a set of all string over 0 and 1 that end with 0011. Now that's different, right? Because if it's end with 0011, then we have to make sure, once you reach 0011, then if we have one more import, then we're going to start over again to make sure we're going to build another 0011 substring. Okay, so that's kind of different. This is never going to end, So this is actually the DFA we just built for example 5. Now example 6. So let us build a DFA for language L, which is a set of all strings over 0 and 1 that don't, all the strings over 0 and 1 that don't contain the string 0011. It's kind of opposite, right? The example 5, which says we tried, it's a set of string that contain the string 0011, but example 6 is kind of opposite. Now we can actually try to build this from scratch, but fortunately we don't have to, because example 5 and example 6 are kind of related. And honestly, if you try to build the DFA for example 6, it's kind of actually difficult. It's kind of tough than example 5 because we want to build all the strings which don't contain 0011. Okay, so looks like there are a lot more cases like this. However, since we already have 5, it's easy to build a 6. Now, do you have any idea what's the best way to do this? Okay.
Professor, we can convert the non-final states into final states, and the final one turns into non-final state. Is that correct?
Okay. So let's say we still follow all the states and the import, just like the previous one, right? Okay,
Yes.
I'm still going to build this. Now, because the question is kind of opposite, build a string that don't contain 0011. So that means everything that, every actually string that doesn't reach E will be accepting string, right? Because once we reach E, then it contains 0011. So once we actually reach the final, final state E, that means this string contains 0011. But we want to build one that does not contain 0011. So every state here, like A, if we reach A is accepting state. Because A, if we reach A only, that means A does not, in state A, it does not contain 0011, right? So if we reach B, so that means either it's 0 or 10 or 110. So once we reach B, that means we may actually, circle the 1 many times in A. And so it could be like a 110, and then we reach B because 1, you're going to actually reach A. 1 again, you still stays in A, and when we got 0, and you would reach B, and this string does not contain 0011. So B is also accepting state, right? What about C? C is also accepting state, okay? And D is also accepting state, okay? Now once we reach B, if we go back to A, it's accepting state. If we reach D, and then we don't get 1, we get a 0, that's good because then we go back to B. So that means this is still accepting state. Now, only unfortunate case is we actually go all the way and finally we reach E. Once we reach E, that means that string contains 0011. So that's not an accepting state, right? Now, once we reach E, so that means after actually we reach E, no matter how many imports we have, that string always contains 0011. So E is actually what is called dead state or trap, right? So as far as, okay, C, once we got C, if we still got a 0, then we stay in C, and it's still accepting state. So it's just opposite. You change this double circle to single circle and change all these single circle to double circle. So once, no matter how many imports we have, as far as we still stays in A, B, C, D, we're still actually, these actually strings still accepted, right? But only when we are unlucky, so we reach E, then we got a string 0011 substring 0011 in that string. So that string will not be accepted by the DFA. Now, once we actually got a 0011, and no matter how many imports we have, that string continue to contain 0011. So that 0011 is still going to be will stay. So that means once we got a 0011, then no matter how many more imports we have, that string will not be accepted. So once we reach E, so E will be a trap. Does it make sense? Okay, if you don't have a question, I would say that so everybody agree with me, right? Okay. Yeah, so that's the solution. And I think that's the last slide for the module 7. Okay. Now let's actually start the next module, module 8. So in module 8, we continue gonna actually work on the finite automata, but mostly we're gonna actually talk about the non-deterministic finite automata, NFA. Okay. Now, I think NFA is pretty similar to DFA. It's very similar, but there's major differences. That difference is the transaction. Okay. So in NFA, we also have phi 2. Okay. The Q, which is a finite set of states. So it's a finite set of states. A, B, C, D. We normally use A, B, C, D, or E, right? Okay. Now sigma is the alphabet of import symbols and the machine will use. So most likely, for the digital computer, normally we use the binary system. So the sigma going to be 0 or 1. But the sigma could also be alphabet, like A, B, C, right? So also it's a input symbols the machine going to use. Okay, and the Q0, just like the DFA, it's a special state, start state, So Q0 is in Q, which is, okay, so it's one of the state over here. Now, typically, we're going to start from the state A, right? Because that's the easiest one. Now, F is a set of accepting states or final state. Okay, so F could have 1 or 2. Now, in the last case, example 6, we have 4 accepting states and 1 trap state. Okay. Now, the last one, delta is the transaction function. Now, the transaction function is different. Okay. So remember, for DFA, the deterministic finite automata, the transaction function is defined like, so you have a value like a current state, okay? And also you have an import value. Now, if the current state is A, if the import value is 1, then this transition gonna actually lead us to a next state, right? It could be B, okay? But next state also could be A itself. You can actually stays in A, so that's possible. But the transaction basically requires two initial value. One, it requires the current state value. What is the current state? And two, it requires the import. If we use actually binary number 0 and 1, then the import could be either 0 or could be 1. Okay. Now, once you have the current state, and once we have the import value, then the DFA gonna lead us to a next state. Okay. That's DFA. Now, the difference between DFA and NFA is, if you look at this word, it's non-deterministic. Deterministic basically means once you got a state, once you got an import, you were guaranteed to have a next value, next state. Okay. The next state could be different, could be the same. Okay. And also for each import, the next state is determined, also decided already. So the next state will be uniquely determined by the state plus the import. Okay, so it's deterministic. The non-deterministic basically means, okay, so the transaction function delta also requires the state and also may require import, or may require state, or may require import. So once you have a current state and a current import, then we may actually go to the next state. But in this case, it's non-deterministic. So that means if the current state is A, if the import is 1, so the next state could be B, could be A itself, could be C, or could be both B and C. Okay, so it's not really uniquely determined. You know, the next state will not be uniquely determined by the current state plus the import. So that's why it's called non-deterministic. Okay, you see the difference here. It sounds like it's very complicated. Let's take a look, you know. So the main difference between DFA and NFA is that for a particular import symbol, okay, the machine can move to any combination of states or move to nowhere. Not just the next state. It could be actually moved to, could be actually run into, into nowhere. So in other words, the exact state to which the machine moves cannot be determined. So that's why it's called non-deterministic finite automata. Now let's actually take a look at the example. So in this example, we'll see that there are 3 states, A, B, and C. Okay, now A is a starting state. Okay, now if we have a current state A, okay, so the current state is A. And if the import is 0, if the current state is A, and the import is 0, then what's the output? What's the next state? Let's see. So suppose the current state is A, import is 0. Okay, the state. And also import. Now what is the next state? Current state is A, import is 0. Then we see that for import 0, because you can actually stay in A, right? Because with import 0, you can stay in A. But also, here's also a direction for the import 0. So with import 0, we could actually also goes to B, right?
Yes.
Yes. So that's why for import 0, and unlike DFA, so with current state and import, the next state is determined. It's going to be unique. Okay. But this time, you may have two directions. Okay. Now, if the current state A and the import is 1, it still could be A, right? And it still could be B, right? And could be C, right? So if it's A, the destination state could be still A, could be B, could be C, because one is appear in three all the transactions. Okay. Now there's another case. Okay, it's called what is this called? Epsilon. Okay. Now epsilon is actually, it's normally we call these null import. So that means A could actually transition to C even there's no import. Okay, so null import means no import. Now, so that means if there's no import, I'm gonna say it's epsilon. Okay, so if there's no import, it could also transition to C. Okay, that's very weird, right? So that's the other cases. So we have, if we have import, 0 or 1, then we're going to do the transition. But for now, for DFA, the deterministic finite automata, if there's no import, there will be no transaction. So it could stay in A, right? But now if there's no import, now suddenly A still could be actually transaction to C, okay, without any import. That's the difference. Okay, so there's actually one more value called epsilon. Okay, epsilon is a value, but it basically means it's empty import. Okay, means there's no import. Okay. Okay. Now, if we want to study one more, then if the current state is B, so which is the actually accepting state. Now, for B, if the import is 0, it could stay in B, right? Because import 0, it could stay in B. Now, I think that's it, right? If import is 1, it goes nowhere. Now, if it goes nowhere, we use another notation called phi. And if it goes nowhere, we could use another notation called phi. Okay. Oh, if it's 1, it still actually stays in B. I'm sorry, this is not phi. If it's 1, then it stays in B. That's it. Okay. That's the only edge from B to other place. Then all the other edges actually coming into B. Okay. Now, if the current state is C, then what's the difference? Let's see. If the import is 0, we're going to go to A. We could also go to B, right? Because it's a 0 here, 0 here, and that's it. Okay. If it's 1, sounds like if it's 1, it's going nowhere, right? So we go to phi, which means we're not going to go into any other state. We just go nowhere. Okay. Because there's no transaction tells us that if the current state P is C. If the import is 1, it doesn't show us that the where you're going to go. No, actually, but that's not happening in deterministic finite automata. For deterministic finite automata, you have to decide what is the next state for each of the import value, 0 or 1. You cannot miss any of this. But in this case, for 1, if the current state is C, if the import is 1, it's not defined. What's the next state? The next state is not defined. So that means the next state is phi, which means it's nowhere. It's go to nowhere. Not any of the state. Okay. Now if there's no import, then C could actually go to B. Okay. Yeah, that's here. C could go to B. So that's the strange things about non-deterministic finite automata. Okay. So in this case, the current state and the import cannot determine the next state. The current state and the import cannot determine the next state. With current state and the import, it can go to A, it could go to B, or it could go nowhere. Okay. For example, if the current state is A, then with the import 0, there are 2 possible states, A and B, right? Like I say. Okay. So this is actually the transaction function. If the current state is A, if the import is 1, then we go to A, B, or C, right? We go to A, B, or C. If the current state is 0, we go to A or B. A or B. If the current state, okay, if the current state is A, but there's no import, then there's still a possibility that the A could go to C. So that's kind of different from the active DFA. But with non-deterministic finite automata, we're still going to be able to decide what is the accepting string, what is the what's the rejecting string. Okay, we're going to talk about this a little bit later. But in this case, things are a little bit more complicated. Now we don't have a unique path that's either lead to the accepting state or lead to a trap state or lead to nowhere. Okay, so there's no um, a unique path, because for finite DFA, the deterministic finite automata, once you are given an import string like a 0 0 1 1 1 0 1 1, one of the string, then you can actually just follow this finite DFA, and you can actually, it's going to lead to a sequence of state, and you can determine what's the final state with that string. But in non-deterministic finite automata, if you are given a sequence of input 0 0 1 1 0 1, it may have multiple paths. Okay, all the paths may work. Okay, so that's a difference. So now let's study the transition delta a little bit more. Let's see how we're going to actually define the transition. Okay, so because the transition delta A is the major difference between DFA and NFA. Okay, now with the NFA, if the set of the state is A, B, and C, then for each state and the import, the machine can potentially go to phi, which is nowhere. Okay, it is not going to go to any of the state. It's just it's finished. Now, if with the current state and the import, it could go to any of these states. It can go to A, it can go to B, it can go to C. Or it can go to A and C and B. It can go to A and C. Or it can go to A, B, and C. Or it can go to 3 different states for the same import value. So the destination state could be all 3. So instead of unique one, like a DFA. Okay, so that means in that particular case, how many for each actually state and import, like a state A and import 1, import value 1, the machine can actually potentially go to A itself, or go to B, or go to C, A and B, A and C, B and C, or A, B, C, all of them. So how many destinations, how many actually different combination of this? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, right? The total of 8. There's a total of 8 possibilities. Okay. Which is actually 2 to the 3. Okay. Now 3 basically means because we have 3 different states. So it could be actually go to nowhere, or could be go to all 3 states. Okay. Now if I have 4 states, if I give you 4 states, Q equals A, B, C, D. Now, for each state and an import, how many different possibilities? How many actually possibilities machine can actually go to? I hope
16.
Okay, 16. How? Let's see. It can go to nowhere. Okay. It could go to A, could go to B, could go to C, and it could go to D, right?
Yep.
Just one single. And it can go to
AB.
Yeah, suppose A and B. Okay, both A and B. It could go to both A and C, or A and D, right? And then B and C, and B and D. B and B and C, B and D, and C and D. So it's possible that it can go to 2 states, and there's total of 1, 2, 3, 4, 5, 6 different combination for 2 states. Now it can actually potentially go to 3 states. So A, B, and C. A, B, and D, right? A, B, and C, A, B, and D, and then B, C, D. B, C, and D. Okay.
A, C, D.
Anything else?
A, C, D.
Okay. A, C, and D. Okay. That's all the possible 3 states. And the last case is all A, B, C, D, right? All of the state. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have a total of 16, which is actually 2 to the 4, because you have 4 states. That sounds complicated, right? Okay. Now, in general, Now the reason why it's actually 2 is because the import value has 2, okay, 0 or 1. Now, in general, if the number of state is q, which is actually like in this case, it's q is n is 3, or in this case n is 4, then the machine can potentially go to 2 to the n. Okay, if q has 4 states, then it's 2 to the 4th, and if q has 5 states, and then it's 2 to the 5th. Okay, now this explains why the transition function is defined as q, that's the number of states, and plus the import. The import gonna be gonna contains all the alphabet in the sigma plus no import. I use epsilon. Okay, so it's a e sigma, union epsilon, which actually lead to 2 to the q. So it's actually q is the n. Okay, there's a 2 to q means 2 to the q possible, 2 to the q possible output. So could be actually any of these. So there's a 2 to the q different possibilities for this transaction. Okay. So that's one difference. The transaction for each state plus the import, the transaction function going to lead to no state or one state or two states or three states, depending on how many states we have, and a combination of all different states. So that's one difference. The other difference is that the NFA can move to next state without import string. Okay, without import string. In this case, we use epsilon to represent no import string. Okay, and also an NFA can move to nowhere. We use phi, none of the state in Q. So that means it's moved out of this machine. Okay, so then this machine contains 3 states, but it just moved to none of these states, just moved to nowhere, move outside of this machine. So that's another possible output. So that's the NFA. Now, how are we going to work with the NFA? So we can draw the NFA, and we still can actually, the NFA is still a finite state machine, but it's non-deterministic finite state machine. And with this finite state machine, it's still going to accept a string, take the import, and it's still going to actually decide whether I'm going to accept the import or I decline the import, just like a DFA. Now, how are you going to do this? So let's see. First, let us build an NFA that accepts string that contains 0, 1 as substring. Okay. Now let's take a look at this example. So we want to build a that's example 1, right? So if we want to build the NFA that accepts strings that contains 0, 1 as a subword. Okay, let's see. We have A. Okay. Now, if the first import is 0, then we go to next state, B. Okay. If we got a 1, we go to next state, right? And that's accepting state. Okay. Now, So what about if in the first import is 1? So we can still stay in 1, A, right? Okay. Now, there's a possibility that if the string is 0, 1, 0, 0, 1, 1, 0, 1, okay. So in that case, looks like we have contains 1. So it's 1, right? Now, what about this one? 0, 0, 1, 1, 0, 1. So we have 0, 1. So this is still going to be accepted, right? Because it just contains 0, 1 as a substring. So in this case, so we have a 0 initially, but because next one is also 0, so that means this is not going to be accepting subword. So in that case, I can actually, let it stay in A, right? Until just if you have a multiple 0, and all these 0, 0, 0, we can stay in A, and until the 0, and right after 0 is 1, then we can go to B. So you can also go to this, and if it's go to B state, and the next one 0, we can stay is here, right? And if it's C, we can actually, once we got the sequence 0, 1, then you can accept any sequence. Once you have 0, 1, then any follow-up import really doesn't matter anymore. Okay. So in this case, this is very similar to the DFA, but it's not a DFA. Why? This is not a DFA. Why it's not a DFA?
Because for the input we are staying at the same state, but in the DFA we go to another state.
Okay. If the current state is A and the input is 0, then the next state could be B or could stay in A, right? So there's two possible values. Okay. There's two possible values. Okay. So that's why it's a non-deterministic finite automata, because in this case, 0 with input value 0, it can go to either B or stays in A. So that's not. But this is going to solve the problem. This is really non-deterministic finite automata. Okay. So let's actually draw this the delta, the transaction function. Okay. So let's see what is the transaction function. Okay. Now, if there's no import, what are we going to do? So there's no epsilon in this case. Okay. So then we're going to say it's going nowhere, right? It's not going to go anywhere. Okay. Now, if the input is 0, where are we going to go? It could go to A or
B.
B, right? Now, if it is 1, it's A. Okay. Now, if the current state is B, so it's going nowhere. Okay. And if it's 0, stay in 0, or stay in B. And if it's 1, then we go to C, which is the final state. Okay. If it's C, then if it's no import, we go nowhere, so we don't go anywhere. And if it's 101, we stays in C. Okay. Now let's check. How are we going to check the, whether, a string will be accepted by the finite machine or not? Okay. Let's just check this. Let's take a look at this string. Okay. So now the difference in this case is we start from state A, right? Now, if the first import is 0, now with 0, import 0, where are we going to go? We can either go to A, right? Or we can go to B, because the output could be A or B. If the current state is A, and if the import is 0, we could go to A or B, right? And then if the next import is 0, now if we go to this branch, if the next import is 0, like this one, where are we going to go?
A or B.
Okay, there's still more branches, A or B. Okay. Now, also for this branch, if the import is 0, where are we going to go?
B.
B.
Stays in B, right? Okay, let's say stays in B. Okay. That's this level. 0, 0, 0. So you may have 3 different branches now. Now next one import is 1, right? So then you have to check each of the branch. If it's 1, A in original, the current state is A, and the import is 1, then we stay in A, right? Now if it's B, import is 1, and we go to C, right? If it's B, import is 1, we go to C. And this is actually the same. It's 1, we go to C, right? Okay, so that's the next 0, 0, 1. Now next one is 1 again, so we stay in A. Next one is 1. Its current state is C. For 1, we stay in C. And this is also 1, we stay in C. Okay. So it's a 0, 0, 1, 1, and the last import is 0. The import is 0. The current state is A, import is 0, so we have 2 branch, A and a B, right? Now, if it's 0 or C, we stay in C. We stay in C. Okay. Now, let's check each of the path. Okay. We check each of the path. I'm going to use different color now. I use the color. Okay. So let's take a look at this path. So the final state is A. That's not accepting state, right? That's not accepting state. Because the accepting state is C. C is the accepting state. Okay. Now let's take a look at the next path. Here, go this way. Oh, so there's another path. Go this way. We got a B. Also no, not accepting state, right? And then we go to here, here, go down, then that's good. That's accepting state. And here we go down, down, accepting state. Okay. We have two accepting path and two, non-accepting path. So that means we will accept it. Okay. So this is accepting. The machine gonna accept this string. Now, in non-deterministic finite automata, now in this case we have two paths which actually leads to two paths which lead to accepting state, which is good. However, as far as we can find at least one accepting state, at least one path that leads to accepting state, then we're going to accept this path. We're going to accept this import string. Okay. Let me say it again. So whether we can accept the import string or not, it depends on all the paths we're going to go through. Because in non-deterministic finite automata, we're not going to go to a unique path like just one A, B, C, A, B, D, or whatever. And eventually we can decide whether the final state is accepting state. But in non-NFA, you may actually end up with a couple of different passes. Unless all the passes are leading to non-accepting state, then we decline the import string. As far as we find one path that leads to an accepting state, then we accept the import string. Okay, so that's basically the difference between DFA and NFA. Okay, DFA, there's only one path. We accept the path, we accept it or not accept it, depending on the final state, the last state. Now for non-deterministical, we may actually lead it like a kind of a structure, like a tree structure. So it's initially start from one state A, and then we're gonna have multiple branches. Now each branch is gonna lead to a different path. Okay. So as far as one path leads to an accepting state, then we accept the import string. Let's take a look at another example, the second example. Okay, 110. Okay, let's take a look at the 110. So we have an A. So, okay, the first import is 1, right? So with A and a 1, so A and a 1, we go to A. Okay. So then next import is, again, it's 1. So with the current state A, and import is 1, we go to A. Okay. And the next import value is 0. So with 0, we have potentially two destination, A or B. So 110, we actually end up with A or B. This is not the final state. This is not a final accepting state. So then we're gonna decline 110. Okay, the machine gonna decline 110 or reject 110. Now what about this?
I accept.
Accepted, right? We have 1, so go to A. And next one 0, so we go to either one branch to A, one branch to B. And then the next one's 1. Next one is 1. And this stays in A because B with 1, B go to C. So this is going to be accepted. This is going to be declined, right? The top one going to be declined. The bottom one going to be accepted. So we're going to accept it. Okay. So we're going to accept this one, and this one we reject. The machine going to reject the middle one. Okay. So it's a little bit more complicated because when we actually, determine whether the machine going to, accept or, reject the import string, we're going to build up all the possible path. Potentially, if the transaction function going to lead to all the different states, then we're going to actually build up all the different paths. So the more state is going to, the more path we're going to have. Okay. So that's the, let's see. Example 2. Let's just build a NFA for language L1, set up all strings over sigma that start with 1. Okay. We have A. Okay. So start with 1. That means if we have a 1, that's good, right? So we're going to accepting state. Okay. And once we have 1, we go to accepting state. Once we are in the accepting state, any follow-up value will be accepted. Okay. But once it's 0, we can actually stay in here, right? Or we can actually say go nowhere. That means that we stay in A. Okay. We're not going to go anywhere. So we stayed in A. So you can actually, you can either put it like this, or you don't have to write. For non-deterministical, you don't have to, draw any line here. So I can actually saying I don't need to draw anything. Now let's take a look. Check that so let's actually do this. So if it's 0, we're not going to go anywhere. So basically, okay, we can still actually stays in A.
Professor, it's phi, right?
Pardon me?
For 0 input,
Oh, it's a it's
phi.
yeah. Oh, I think this is 1. Sorry. And then if it's 1, then we go to B. That's a final accepting state. Now, if it's B, then we stay in B. Okay. So, yeah, I think that's pretty much it. Okay. Now, next thing we're going to talk about is the difference between DFA and an NFA. Now, the difference is the delta, the transaction function. But also, we can think about the DFA and NFA So actually, NFA could also include DFA, right? Because NFA just say the transition function can be, can lead actually to one state or lead to nowhere, so it's just staying where you are. Or the transition function can lead to two states or three states simultaneously. But DFA just say for every state and the import, you have to lead to one state. So in that case, so DFA should be included in the NFA. So that means if you actually try to, draw the NFA, and if you already draw the DFA, and you can take this as a NFA, right? And it's one of the, so that means for any actually, problem, if you try to build any actually finite state machine, you may have a multiple solution for that, for that state machine. So if under certain condition, you can build a multiple solutions. Now, including if you build a DFA, that DFA can take as one of the solution for NFA. But NFA actually is more flexible. You can include more different solution. So that's why it's not hard to show that every language accepted by DFA can be accepted by some NFA. That's because NFA is actually it's a relaxed form of definition of DFA. So that means DFA itself also is also an NFA. Okay. Now let's take a look at the next example. So let's see. So we want to build both DFA and NFA to see what's the difference. Okay. So these actually finite state machine DFA and NFA will accept binary string. So that means 0 or 1. That end with 0, 1. We want to build a binary string that end with 0, 1. Okay. So let's first take a look at DFA. With DFA, if we have a start state A, okay, then if the import is 0, then we are closer to the accepting state, right? So we go to next state B. B is closer to the accepting state. Now, if we actually start with 0, if the import is 0, then maybe we can stay in A, right? We don't move forward because import is 1, then the first import is 1, then this has nothing to do with 0, 1. So we want to stay in A until we find a 0. Okay. Now, if we are lucky, the next one is 1. So we got the final state or the accepting state. Okay. But we have to make sure it's actually end at the 0 and 1. Okay. Now, if the next one, for next import, if we have one more import, now if the next import 0, 1, well, next import is 0, that means this string does not end with 0, 1, right? So then what we do? If it does not end with 0 or 0, 1, if the next import is 0, we're already in C because 0, 1, that's actually land in the accepting state. But if the next import is 0, then this can actually move away from accepting state because it's not accepted, right? But there's a potential that it's still going to go back to the accepting state because if the next one is 1, then it's still going to be okay, right? So where are we going to go?
A.
We can go to A. We actually can go to B, right? Because if after C, 0, 1, if we got a 0 at the next one, all we need to do is to get another one, right?
Yes.
So we just need to go to 0. Okay. Now we do need to go back to A only when the import 0, 1 and the next import is 1. Then we cannot go to B, because if we got a 1, if next one is 1, so then we have to rebuild 0 and 1, right? We have to rebuild both digitals. So we cannot go to, we can definitely, if it's 1, we cannot go back to B, because if we got 1 again, so then we have a 1, 1, then we're gonna accept it. So that's not true, because 1, 1 does not end with 0, 1. So now we're gonna go back all the way back to the original, right? We start to build this 0, 1 again. Okay. So now, so we have state A. If it's 0, we go to B. If it's 1, we stays in A. Now for C, if it's 0, we go back to B. If it's 1, we go back to A. For B, if it's 1, we go back to C. Now what about if we have 0 at B? Because for each state, we have to actually decide for each import where we're going to go.
Stays in B.
Yeah, we stays in B. So that's the DFA. For DFA, remember, for each state, we have to decide where we're going to go. If for the current state, we have to decide where we're going to go for each import value. Okay. If there are two imports value, 0 or 1, import values 0, 1, we have to decide where we're going to go for 0, where we're going to go for 1. You cannot miss any of this. You have to decide it. So that's why it's called deterministic. But for now, deterministic finite automata, things could be different. You don't have to actually have a value for each of the in state. For each of state, you don't need the import value. Or for each of the state, if you got import value, you don't have to go to a unique state. You can actually go to multiple different states. Okay, so now let's say NFA. So let's for A. Okay, now the easy path is this, right? So we got to see. If it's 1, we can stay in A. And if it's 0, we can also stay in A, right? Because if it's at 0, 0, 0, 1, that's still okay. So that means you can still actually, so because it's non-deterministic, so for each of the current state, we don't have to go to a unique state. So for 0, we can go to B, and we can still stay in A. What else we need to do? We don't have to define anything, right? For B, if it's 1, we go to C. For 0, we can go to nowhere. So that means we don't go anywhere. So don't go to nowhere. So that means stay. Okay. So That's the let's take a look at the next one. Example 4. Build a DFA and an NFA to accept the binary strings that start with 0. Let's build up DFA, and then we're going to have a break so you can decide what's the NFA. Okay, let's build a DFA. So accept a binary string that start with 0. Okay. Okay, if it's 0, that means it starts with 0, right? So we accepted it. We accepted this. Okay. Deterministical. So then we have decided if we go to 1, what does that mean?
Dead state.
C. And that's a trap, right? So it doesn't matter whether it was 0 or 1 because you already started with 0. Basically, you only accepted a string with start with 0. Now, if the string does start with 1, it doesn't matter how many actually follow-up digitals we have. It's always the trap state, right? So this case, if it start with 0, then it stays in the accepting state, right? So that's the DFA. Now, what is the NFA? Okay, so I think let's take a small break. I'm going to give you 5 minutes. So let's actually start again at the 9:05. So I can give you a little bit more time. So let's actually stop the recording now. So we'll be